Now, for this equation in discrete time, you can also solve it following a similar procedure as before. Okay, you can start by looking for a particular solution and also a homogeneous solution, a solution to this equation here, and adding them up to form a solution for this. Okay, and also you can specify the condition of initial rest, right, to make this solution unique. Okay, so here you're solving the problem following similar approaches as in the continuous time case. Okay, so you could do that. Okay, so this is one way to solve for this nth order linear constant coefficient difference equation in discrete time. But in discrete time, there's actually a more convenient way to do this. Okay, by sort of playing around with this equation here. Okay, so in discrete time, right, sometimes you can obtain a more convenient solution by viewing this equation as this recursive equation here. Okay, so what I'm doing here is that I'm just taking this equation, I'm leaving only the term y of n on the left-hand side and moving everything else to the other side. Okay? Right? Now, by writing the relation in this so-called recursive form, okay, you obtain a more straightforward way of obtaining the output signal yn. Okay? So what this form tells us is that as long as you know what is the value of x, okay, and the value of y of all n previous times, then you can obtain the value of y at time n. Okay? So for example, if you want to solve y0, okay, you can do this with knowledge of xn for n greater or equal to 0, and knowledge of y minus 1 to y of minus n. Okay? And if you're assuming the condition of initial rest, then these values would be 0, right, if the signal does not arrive before time 0. Okay? So from this recursive equation, we can see that we can compute y0 as long as we know x and also know y for minus 1 up to minus n. So all previous n, capital N time instants. Okay. Now once you solve y0, you can then solve y1 because you know what x is and you know what y0 to y of minus n plus 1 is. Okay? And you can continue in this fashion. You can solve y2 because you have y1, y0 up to y minus n plus 2. Okay, and so on and so forth. Okay. So this is an alternative way of finding the output signal explicitly in the discrete time case, right? Just following this recursive equation step by step, okay? So we can look at an example. Okay. So suppose that we have this first order difference equation, okay? So yn is equal to minus 1 over 2, y of n minus 1 equal to x of n, okay? So if you want to solve it using the approach we just mentioned, you first try to write this in the form of a recursive equation. So you write yn on the left-hand side, and then you have xn plus 1/2 yn minus 1 on the right-hand side. Okay. Now, let's assume, right? Let's assume, consider an input signal x that is just a scaled delta function. So suppose that xn is just some scaled impulse, okay? So xn here is something like this. Right? And also, let's consider the condition of initial rest. Okay? So the condition of initial rest means that since the input does not occur until time 0, the output must be 0 for all n that is negative, okay? So this implies that y of n is equal to 0 for n less or equal to minus 1, since x of n is 0 for n less or equal to minus 1. Okay? So then, following this recursive equation, we can start to specify the values of y for all n that is greater or equal to 0, okay? So starting from time 0, we know that y0 is equal to x0 plus 1/2 y minus 1, okay? Now, y of minus 1 is 0 due to this condition of initial rest, and x0 is just k. So this is equal to k, okay? Now continuing in this fashion, y1 is x1 plus 1/2 y0, okay? Now x1 is 0, right? And y0 is k, so this is 1/2 k, okay? And similarly for y2, we get x2, which is 0, plus 1/2 y1. So this gives you 1 over 2 squared, 1 over 2 squared times k. Okay? So, by induction, you can show that yn, which is xn plus 1/2 yn minus 1, it just is just 1/2 to the power n times k. Okay? And so on and so forth. Okay? So using this recursive form, okay, we can directly, infer the output signal, right, one by one by induction. Okay? And this is, much more straightforward than having to, guess the particular solution and the homogeneous solution, and solving their corresponding coefficients. Okay. Now, looking at this, right, what is the impulse response to this system? Okay. So what is the impulse response to this system? Okay. So the impulse response is the response to an impulse, right? So this means that the impulse response is the value of y when x is simply equal to a unit impulse, right? Which is the case where k is equal to 1. So your impulse response, in this case hn, is just this value here for k that is equal to 1. So this is 1/2 to the power n. And this is only for n that is greater or equal to 0. So we multiply it by a unit step function. Okay. So for an impulse response that has values in infinite number of terms, we call this an infinite impulse response. Okay. So this is a system with infinite impulse response. Okay, or IAR for short. Okay. So this is typically the case when you have a difference equation with order capital N greater or equal to 1. Okay. So if you have a difference equation where the order capital N is greater or equal to 1, the impulse response of the system is typically infinite. Right? You typically have an infinite impulse response. Okay. Now in the special case where capital N is equal to 0, right, in which case this term is 0, and therefore yn is just equal to this weighted sum of time-shifted x, then the impulse response, right, would instead be just equal to this, which is finite. Okay? So if capital N is 0, we typically get a finite impulse response. Whereas if the order capital N is greater or equal to 1, then we usually have an infinite impulse response. Okay. Now to obtain a better insight on what a system of this type would look like, right? It's often convenient to plot out the so-called block diagram of the system. Okay? So a block diagram, right, is something that helps us visualize what a system looks like, right? So that we gain more intuition from it. And also it sometimes helps us to understand how to implement it in practice. Okay? So using this example that we just looked at, I suppose we have a system where the input-output relation is this yn plus a, yn minus 1 equal to b times xn. Okay. Now, our goal here is try to plot this input-output relation using a general block diagram. Okay. Now, if you look at this equation, there are three basic components here. One is the addition. One is multiplication, okay, by a scale A or a scale B. And the other is this delay by 1 unit time. Okay. Now, in a block diagram, we're accustomed to representing summation or this addition with this circle and a plus inside. Right? So if we want to produce x1 plus x2, we take x1, x2 going into this block here. Okay. Now, for multiplication, right, we sometimes just draw this arrow with the scale labeled on top. Okay. So this is addition, and this is multiplication by a constant. Now, other than just labeling this other than just labeling this A on top of the arrow, right? Sometimes I like to write it more explicitly, right? To draw it more explicitly with a block multiplied by A. Okay? Right. So sometimes you will see this, and sometimes you will see this. Okay? And then the third one is the delay. Okay? So this block with a D labeled by D means that we're delaying the input by 1 time unit to give you x of n minus 1 at the output. Okay. So this difference equation here can be plotted with the combination of these three basic block components. Okay. Now, suppose we first write this in terms of a recursive equation where we have yn equal to bxn minus a y n minus 1. Okay? So what this tells us is that the output should be equal to the input times a scale b. Right? So suppose we have an input xn times a scale b. Okay? And this should be, right? So the output should be equal to this input times b plus a delayed output times minus a. Okay? So we want to add it. Okay? So we want to add it with a delayed output multiplied by scale minus a. All right? So this block here gives us the effective system between input x and the output y. So this block diagram here gives us much more insight on what actually is occurring in the system, right? So what this is saying is that if you have this nth order difference equation, then what this means is that your output would need to take into consideration capital N delayed outputs from the past. Okay? So a system with satisfying this differential equation here is actually a feedback system, okay, that takes the output from the past to produce the input, to produce the output at the present. okay? So this is the case when we just have a first order difference equation. Okay. So you can do something similar for continuous time as well. Right. So suppose you have this differential equation in continuous time where the input-output relation is this derivative of y plus a scale of y of t equal to a scale of the input x of t. Okay. So again, there are three basic components here: the summation, the multiplication by a scale, and the differentiation. Okay. So the addition and the multiplication is expressed similarly as in the discrete time case. But in the continuous time case, we sometimes use this d here, this d block here, to represent the differentiation rather than the delay. Okay? So here d is used to represent differentiation. Now this is sometimes confusing. So for myself, I often like to use a block like this instead. Okay? So to avoid confusion, I often like to use this block for differentiation rather than just this d. Okay? But it really depends on the person. Right. All right, so now we want to put together these three blocks to represent this differential equation. Okay, so let's first, again, reorder the terms to get y of t equal to b over a x of t minus 1 over a, the derivative of y. Okay? So similar to before, this is saying that the output should be equal to the input, x of t, scaled by b over a, added with something that is equal to the output through a differentiator, scaled by minus 1 over a, and added back to the input. Okay? So this is the differentiator. Okay? And this is the effective system that we're looking at. Okay. Now, this is not the only way you can plot the system diagram. All right. Now, alternatively, assuming that y of minus infinity is 0, okay? So suppose that y of minus infinity is 0. In that case, when you integrate the derivative of y of t, you will get the signal y of t exactly, okay? So in that case, y of t, okay, can be obtained by integrating this, which will be equal to the integral of minus infinity up to t of b x of tau minus a y of tau d tau. Okay? So what I'm doing here is that now I'm instead moving this term to the other side and then integrating up to time t. on both sides, okay? So if you integrate the derivative up to time t, you get y of t. And then on the right-hand side, you have b of xt minus a times y of t integrated from minus infinity up to t, okay? So if you view it this way, then your system diagram would instead look something like this. All right, you take x, you scale it by b, right. You add it to minus a scale of the output, okay? So you add these two together, and then you pass it through a integrator. Okay, so this is a integrator. All right. And this system gives you the same effective input-output relation, okay? Right. So plotting the equation using a system diagram, right, on the one hand helps you gain some intuition about what is really occurring inside the system. But on the other hand, it helps you sort of think of how to implement this in practice, okay? So, here, drawing the block diagram in these two different forms tells you that there are two different ways to implement this system to get the same, input-output relation, right? So you can either do it using a differentiator, or you can do it with an integrator. Right? And sometimes one approach is less costly than the other approach, okay? So depending on which one is more convenient for you in terms of cost or computational complexity, you would tend to use that, the corresponding one, okay? Okay. Now, for the last part of this chapter, I just want to, go back and talk a little bit more, right, about our understanding of unit impulse functions. Okay. So previously, in the previous chapter, when we defined the unit impulse, right, if you recall, we said that a continuous time, unit impulse function, we should view as an idealization of a pulse that is short enough so that its shape and duration has no practical consequence. Okay? So this is something that we said before, right? So we say that this impulse function, delta of t, is an idealization of a pulse that is short enough so that its shape and duration is of no practical consequence. Okay. So when we first talked about this, it's probably not very clear what we mean by having no practical consequence. Okay. But now, after understanding what a system is, you now can understand better what we meant by having no practical consequence. Okay. So what we mean here is that, as long as the pulse has a duration that is much shorter than the response time of the system, right? The response time of the system is characterized by how fast the impulse response varies over time, right? So as long as your pulse is short enough compared to the response time of the system, right, it doesn't really matter what the exact shape and duration of the pulse is, the output would still look almost the same. Okay? So instead of dealing with these specific short pulses with various shapes and durations, we instead idealize it into a convenient impulse function, right? And we just need to specify what is the response to this impulse function to understand how the system responds to various short pulses. Okay? Now, previously, we defined this, we viewed this continuous time impulse response as a limit of this rectangular pulse, delta sub delta of t, as delta goes to infinity. Okay. But this does not need to be the case, right? So actually, if our goal is just to get a short pulse that yields the same response at the output, this impulse response, right, potentially can be constructed by the limit by the limit of many different types of short pulses, right? So the specific shape and duration of the short pulse that we're looking at is not really important. Okay, and you can sort of see this through the following example here. Okay, so by the definition of a unit impulse, right, we know that it satisfies this shifting property here. So if you choose x of t as let's say a delta function, then this means that delta of t will be the convolution of delta of t with itself. Okay, so what does this imply? So suppose that we view delta of t as the limiting form of delta sub delta of t as delta goes to 0. Oh, sorry, this should be 0. Okay? And let us define this r sub delta of t as the convolution as the convolution of delta sub delta of t. Okay. So previously, right, when we introduced this delta of t, we showed that we can we can view it as a limit of this delta sub delta of t as delta goes to 0. Okay. Now by the shifting property, we know that delta of t is equal to delta of t convolved with itself. Okay. So if you define r sub delta of t as the convolution of this short pulse with itself, then as delta goes to infinity, the right-hand side converges to this, and so the left-hand side must also converge to this. Okay? So hence, this r sub delta of t converges to delta of t as delta goes to 0. Okay. So what this tells us is that even though at first we viewed delta of t as a limit of this rectangular pulse as delta goes to 0, through this derivation, you can actually show that this delta of t actually can be equivalently viewed as a pulse r sub delta of t for delta going to 0. And r sub delta of t, which is a convolution of this delta sub delta of t with itself, actually takes on this rectangular shape, which is very different from this original rectangular shape, right? So it takes on this triangular shape, which is different from this, okay? So this gives you an example of two signals whose limiting form behaves the same as this delta of t. Okay. So following similar argument, you can actually find, infinite number of pulses, infinite number of short pulses that would converge to delta of t in the limit. Okay. So for example, you can take the convolution between r sub delta of t and r sub delta of t. And again, because the limit of this converges to this on the right-hand side, right, this must also converge to delta of t. Okay? Or you could look at the convolution of r sub delta of t with delta sub delta of t, right, and so on. And you will see that all of these behave as delta of t as delta, capital delta goes to 0. Okay? So this tells you that, when capital delta is finite, is non-zero, these short pulses may look very different, right? May look very different when capital delta is non-zero. But as capital delta goes to 0, right, all these different kind of short pulses will eventually behave the same as this impulse function delta of t. Okay? So for us, it's really not important what is the exact shape and duration of this pulse as long as it behaves the same asymptotically. Okay? Now we can sort of see through the following example, what we mean by having a pulse that is short enough so that the shape and duration has no practical consequence. Okay? So in this example here, we have a system where the input-output relation can be written like this. Okay? Now here we have the response, right? Here we have the value of y of t when the input x of t is chosen as 4 different types of short pulses. So this is when x of t is this rectangular pulse. This is when x of t is r sub delta of t, which is this triangular pulse. This is when x of t is the convolution of delta sub delta of t and r sub delta of t. And this is the case where x of t is the convolution of r and itself. Okay? So again, these are the values of y when we're looking at 4 different inputs. Okay. Now, when delta is non-negligible, right? When delta is not very small, let's say delta equals 0.5, you will see that the different shape of the input has a significant impact on the shape of the output. Right? So you see here that there is this, peak here for x of t equals delta, right? But if you choose a different x, right, it has a smoother slope, and similarly here. Okay? But as you make capital delta smaller and smaller and smaller, right, so that it approaches the behavior of a delta function, you will see that as long as this capital delta is small enough, eventually these responses, all the responses would look exactly the same as the response to this unit impulse. Okay? So as long as these deltas are small enough, they eventually will behave as this h of t, which is the ideal impulse response. Okay? So regardless of what the original shape of the signal is, as long as the duration is small enough, eventually their behavior through the system will be the same. Okay? Now, how small should capital delta be in order to satisfy this property? Okay? So obviously, this delta will depend on how fast the system responds. Okay? So in this case, our channel responds as a exponential to the minus 2t. Okay? Now, if you change the coefficient here from 2 to 20, then the impulse response would be e to the minus 20t, which decays much faster than the previous case. So because in the case where the system responds much faster, you would need delta to be much smaller in order for them to eventually look the same. Okay? So this is much smaller than 0.0025, as we saw in the previous example. So this is just an example to give you a better understanding of why we can look at the impulse response, right, as an approximation of, general the response to general short pulses in practice. Okay, so as long as the duration